Welcome back, everyone. Industrial heat sits at the center of modern manufacturing, even though industrial heat rarely draws attention. Factories apply steady, high-temperature heat to shape metals and cure composites, while maintaining continuous processes. This heat functions as a constant input rather than an intermittent input. Production lines assume continuous heat availability. In most factories, production planning assumes a stable heat supply from hour to hour. For decades, factories produced this heat by burning natural gas inside industrial boilers installed on site. This configuration fixed heat production, fuel delivery, and production schedules into a single operating system. When gas supply remained stable, production continued as planned. When gas supply was interrupted, production stopped. This dependency defined industrial energy planning for generations. Today, this dependency is beginning to loosen. A new class of systems supplies industrial heat without combustion. These systems operate in active facilities and connect directly to production environments. Their presence changes how factories schedule heat delivery, control timing, and assess operational risk. Industrial heat batteries are systems that store energy directly as heat, rather than storing energy as electricity. At introduction, these systems are operational in select industrial facilities and are expanding into broader use. Industrial heat batteries separate energy intake from heat delivery. In practical terms, energy intake and heat delivery no longer occur at the same time. Facilities absorb energy when energy is available. Facilities release stored heat later when production requires heat. From the outside, these systems appear as insulated units connected to existing heat distribution equipment. These systems reach the same temperature ranges that boilers traditionally supplied. This temperature range allows industrial heat batteries to serve the same industrial functions. The difference lies in how time relates to heat generation. Heat no longer forms at the same moment heat enters production equipment. In industrial settings where production schedules, energy prices, and grid conditions rarely align, this separation introduces operational flexibility. Operational constraints inside factories drive this shift rather than abstract goals. Industrial operators prioritize uptime because interruptions disrupt materials, equipment, and delivery commitments. Operators also prioritize predictable costs and stable process conditions. These priorities determine how facilities compare energy systems. Natural gas boilers tie uptime, cost predictability, and process stability to external fuel markets and delivery infrastructure. That linkage changes when facilities generate heat independently of immediate production demand. Facilities convert energy into heat ahead of time and store the heat until production requires it. This change breaks the direct coupling between fuel delivery timing and production schedules. The result is a structural change in system design rather than a marginal efficiency improvement. Please subscribe. A major developer in Dortmund has deployed heat battery systems alongside existing boiler equipment. These installations operate as part of daily production rather than serving as pilot demonstrations. Electrical energy enters the system during periods of availability. Electrical energy converts into stored thermal energy inside the system. At this stage, conversion and storage occur before equipment requires heat. Stored energy remains contained until production requires heat input. When demand rises, stored heat flows into existing industrial circuits that serve furnaces, dryers, or reactors. Resistive elements raise the temperature of dense storage materials. Insulation slows heat loss into the surrounding environment. The delivered heat level remains unchanged. Heat generation timing changes. Boilers no longer need to run continuously to maintain readiness. Boilers can operate less frequently or remain offline for extended periods. Reliability drives adoption because industrial processes often operate continuously for long stretches. Interruptions can damage materials, put stress on equipment, and force shutdowns. There are cascading effects that follow brief supply instability in this kind of context. Natural gas systems depend on external pipelines, pressure regulation, and combustion hardware that is located outside the factory boundary. In contrast, Heat batteries operate entirely within the facility. They store energy on site and deliver heat without the need for a continuous fuel flow. This is made possible by thermal inertia. Large heat storage masses cool slowly, and that slow cooling limits short-term temperature variation. Heat output remains stable even if incoming power fluctuates. As a result, risk management shifts away from external supply interruptions and toward internal system monitoring. The set of likely failures changes, and many previously accepted risks diminish in importance. A research organization called Nagoya has evaluated high-temperature heat batteries under repeated industrial cycling conditions. These tests mirror factory operation across thousands of charge and discharge cycles, which is a rigorous approach. This evaluation exposes system behavior under realistic operating stress rather than just ideal conditions. Electrical current flows through resistive elements, transferring energy into dense storage media. When heat is required, the stored energy moves through controlled interfaces connected to process equipment. The immediate outcome is consistent temperature delivery across extended operating periods. Over time, maintenance behavior changes because combustion is absent. Mechanical wear associated with burners and exhaust systems no longer accumulates, which is significant. Service planning shifts toward electrical components and insulation integrity instead. As a result, downtime forecasting and management change as well. Cost behavior accelerates replacement because industrial operators plan across long-time horizons. Energy costs shape contracts, pricing models, and capital decisions. Regional supply conditions and seasonal demand patterns drive natural gas price variation. Heat batteries separate heat costs from fuel price movement by separating energy purchase from heat use. Facilities can acquire energy when prices are favorable and store it for later conversion into process heat. Timing rather than absolute price defines the critical distinction here. Planning and contract structures simplify as volatility decreases, and predictability improves even when average costs remain similar. This improvement really undermines the long-held assumption that gas boilers provide the most controllable and stable heat input available to industry. An industrial engineering firm, Vesteros, has integrated heat batteries into existing production lines without needing to redesign the core equipment. Downtime during upgrades carries a high cost, which makes this integration approach significant. Even short shutdowns can disrupt supply commitments in many facilities. Heat batteries are able to connect to standard heat delivery systems, such as steam loops and hot air channels. The stored heat then transfers into these systems at controlled rates that match the process requirements. The production line follows the same sequence of operations. The origin of the heat just differs. Installation risk decreases because compatibility remains high. Adoption can, therefore, proceed incrementally rather than through disruptive rebuilds. A manufacturing consortium in Ulsan is currently coordinating deployments across multiple facilities to standardize integration practices. This standardization focuses on operating procedures and control interfaces. These elements, in turn, govern how heat batteries interact with existing systems. Variation between installations decreases as coordination progresses. Operator uncertainty during evaluation also declines as a result. Shared practices convert individual installations into repeatable industrial configurations. The transition from experimentation to routine deployment occurs at this stage. Gas boilers are no longer the default choice for new capacity. Selection depends on context rather than assumption. Across industrial sectors, heat batteries are altering baseline assumptions about how heat is produced and managed. The change is quiet but structural. Combustion no longer defines the starting point for industrial heat planning. Timing control and stored capacity now take precedence. Facility design and upgrade decisions change as a result. As installations expand, new facilities are designed with heat batteries as primary systems rather than just auxiliary additions. Procurement decisions, maintenance strategies, and risk assessment across manufacturing shift accordingly. Industrial heat planning moves away from fuel dependency toward internal system flexibility. This transition is already underway and continues to spread through operating facilities. Thank you very much for watching. Please like and subscribe.